What if everything you know about the universe is merely a fragment of a deeper hidden reality? From the tiniest particles to the very fabric of space itself, the cosmos remains a mystery we've barely begun to unravel. Some scientists suggest our reality is not singular. Unseen dimensions, alternate worlds, or even the universe itself as a mathematical construct may hold the answers. These ideas aren't just speculative. They challenge the boundaries of what we consider reality. Why does mathematics so perfectly describe the universe? What if the rules we rely on are merely shadows of a deeper truth? Today we aim to tackle the questions that transcend human understanding. The complexity of the universe has inspired numerous unconventional theories, each attempting to challenge our understanding of reality. Among them are the simulation hypotheses, the holographic principle, and brain cosmology, all offering radically different perspectives on the nature of existence. For example, the simulation hypothesis posits that our universe is not a physical reality, but a complex digital construct. Popularized by thinkers like Nick Bostrom, this hypothesis suggests that an advanced civilization could create simulated worlds indistinguishable from reality. The idea becomes increasingly plausible with the rapid advancements in computer simulations and virtual reality. Consider this. If it becomes possible to simulate entire worlds with conscious beings, the number of simulated realities could far exceed the number of physical ones. By this logic, the probability of us existing in a simulation rather than base reality increases. While this hypothesis remains unprovable, it has sparked debates among scientists and philosophers about the nature of free will, ethics, and even the limits of science. The holographic principle, on the other hand, takes a fundamentally different approach, suggesting that our entire three-dimensional universe could be encoded on a two-dimensional surface. This idea stems from black hole physics, where researchers like Gerard 't Hooft and Leonard Susskind propose that the informational content of a black hole resides on its event horizon rather than its volume. When extended to the entire universe, this implies that everything we perceive as volume in space is, at its core, a projection. Recent studies in quantum mechanics and string theory have explored this possibility, and some models have shown that the mathematics of a two-dimensional universe can indeed replicate the physics of a three-dimensional one. This concept deeply impacts our understanding of reality, raising questions about whether our perception of depth is merely an emergent illusion. Brain cosmology is another intriguing idea derived from string theory, which envisions our universe as a three-dimensional brain, short for membrane, embedded in a higher dimensional hyperspace. According to this concept, other brains could coexist, separated by imperceptible dimensions. Interactions between these brains, such as collisions, might even explain phenomena like the Big Bang. This idea opens up fascinating possibilities. For instance, gravity might appear weak in our universe because it leaks into these extra dimensions. Moreover, if brains can interact, one might wonder whether contact with another brain could explain phenomena we currently don't understand. Let's delve into a less conventional idea: the one-electron hypothesis. Proposed by physicist John Wheeler a bold and unconventional concept regarding the fundamental principles of our universe. According to Wheeler, every electron in the universe could be the same electron, traveling along a single continuous trajectory through time and space. This radical notion is based on the concept of world lines, which represent the path of an object in space-time. In physics, world lines trace the trajectory of a particle or object as it moves through space and time. Unlike the conventional idea of tracking an object's movement in three-dimensional space, world lines incorporate time as a fourth dimension, creating a continuous representation of a particle's existence in space-time. Wheeler's thought experiment emerged during a conversation with his colleague, Richard Feynman. He speculated that an electron traveling backward in time could appear as a positron, the antimatter counterpart to an electron. If true, every electron in the universe could originate from the same singular entity, traveling forward and backward through time. Wheeler envisioned the electron's trajectory as a loop in spacetime. Moving forward in time, it behaves like a regular electron, and moving backward in time, it manifests as a positron, the antimatter twin of the electron. The looping trajectory would weave a tapestry where every observed electron in the universe corresponds to a segment of this unified, interconnected path. In this system, the world line of this single electron twists and turns through space-time, intersecting countless times. And at each intersection, a particle appears as an electron or positron depending on its temporal direction. The unusual concept creates an infinite number of manifestations of the same particle without requiring new particles. This hypothesis, though highly speculative, offers a remarkably simple explanation for why all electrons possess identical properties, such as charge and mass. Wheeler's idea, however, raises questions about the mechanisms enabling such phenomena and the symmetry, or lack thereof, between electrons and positrons. Richard Feynman expanded on Wheeler's concept, proposing that antimatter could be interpreted as ordinary matter moving backward in time. This interpretation, foundational to quantum electrodynamics, suggests that particles like positrons are indistinguishable from electrons traveling in reverse temporal order. This perspective aligns with Feynman diagrams, where particles and their antiparticles can interchange roles depending on the direction of time. While this one electron hypothesis is not a mainstream theory, the concept of time reversal remains a cornerstone of modern physics, offering insights into particle interactions and symmetries in quantum fields. This hypothesis suggests an extraordinary level of interconnection among all particles. If true, it would mean the fabric of the universe is unified through a single particle traversing time. This interconnection implies the existence of a deeper fundamental structure governing all matter, potentially challenging traditional distinctions between individuality and universality in physics. However, this theory faces significant challenges. For instance, the observable universe contains far more electrons than positrons. If all electrons were manifestations of one particle, this asymmetry would require an explanation. The lack of corresponding positrons equally complicates the hypothesis, keeping it largely in the realm of thought experiments rather than empirical science. Now let's explore the equally fascinating concept of superfluid spacetime, which envisions the very fabric of the universe as a superfluid liquid, a state of matter with unique, nearly frictionless properties. This idea emerges as a potential bridge between two of physics' most profound theories: Einstein's general theory of relativity and quantum mechanics. To begin, let's recall that space-time is a four-dimensional structure in which events in the universe unfold. General relativity describes space-time as a dynamic entity that can bend, stretch, and deform under the influence of mass and energy. Massive objects, such as stars and black holes, create distortions in space-time that we perceive as gravity. While general relativity successfully explains large-scale cosmic phenomena, it struggles to integrate with quantum mechanics, which governs the behavior of particles on microscopic scales. Quantum mechanics treats space-time as a chaotic, probabilistic field filled with fleeting particle interactions, rather than a smooth continuum. This is where the analogy with the superfluid offers an intriguing perspective. From this viewpoint, space-time behaves like a superfluid, a special phase of matter with nearly zero viscosity. Superfluidity is best known in helium-4, which when cooled to near absolute zero transitions to a state where it flows without resistance and exhibits counterintuitive behaviors, such as climbing walls or forming quantum vortices. Quantum vortices are tiny, stable whirlwinds in superfluids, where rotation occurs in fixed, quantized steps. Unlike ordinary vortices, they experience no friction and have sharply defined cores due to quantum effects. If space-time operates like a superfluid, its quantum properties might manifest as tiny oscillations or waves akin to excitations in a liquid. These oscillations could correspond to elusive quantum gravitational phenomena that physicists have long sought to reconcile with relativity and quantum mechanics. For instance, gravitational waves detected by LIGO may represent microscopic expressions of such superfluid dynamics in spacetime. The superfluid spacetime hypothesis provides a framework for reconciling the smooth, continuous nature of spacetime and general relativity with the probabilistic, fluctuating nature of quantum fields. In this model, the apparent smoothness of spacetime on large scales is due to its superfluidity, while its quantum properties become evident at microscopic scales. Quantum vortices in superfluid helium bear striking similarities to predicted structures of space-time singularities, such as those in black holes. These vortices could serve as a physical analogy for understanding the granular quantized structure of space-time at the Planck scale, the smallest scale of space, time, and energy, where quantum mechanics and gravity merge, and our current physics breaks down. In other words, it's the size of the building blocks of the universe. Superfluid liquids such as helium-4 and helium-3 serve as experimental platforms for studying potential spacetime behavior. Researchers have observed these liquids mimicking phenomena seen in astrophysics and cosmology, such as quantum turbulence, wave propagation, and even analogs of event horizons. Moreover, the behavior of quantized vortices and rotating superfluids resembles the rotation curves of galaxies, hinting at connections between micro and macro scales. By studying these systems, scientists continue to gain insights into how spacetime might behave under extreme conditions, such as near black holes or during the early moments of the Big Bang. Naturally, speaking of bold ideas, it's impossible not to mention the mathematical universe hypothesis, proposed by physicist Max Tegmark. This theory posits that the universe itself is a mathematical structure. According to this idea, everything in the cosmos, from particles to galaxies, is not merely described by mathematics, but fundamentally consists of it. From this perspective, the laws of physics and even reality itself arise from the properties of mathematical objects. The roots of this idea trace back to antiquity. Philosophers like Pythagoras believed that numbers and mathematical relationships underpin all of reality, famously declaring that all is a number. Plato expanded this notion, suggesting that mathematical forms or ideal objects exist in a timeless realm, shaping the physical world as imperfect reflections. In modern times, Max Tegmark revived this philosophy, asserting that every aspect of the universe corresponds to mathematical structures. And Tegmark argues that at its deepest level, the universe is not made of stuff, but is pure mathematics existing independently of human thought. This hypothesis finds support in the striking mathematical patterns observed in nature. Consider the hexagonal structure of honeycombs, which reflects maximum packing efficiency, a concept rooted in geometry. Similarly, cicadas emerge in prime-numbered year cycles, such as 13 or 17 years, minimizing overlap with predators, a biological phenomenon tied to a number theory. In space, planetary orbits follow precise elliptical trajectories described by Kepler's laws, which are inherently mathematical. These examples demonstrate how nature appears to adhere to principles pointing to a profound connection between reality and abstract mathematics. One of the strongest arguments supporting this hypothesis is the remarkable effectiveness of mathematics in describing and predicting physical phenomena. For instance, Einstein's equations of general relativity predicted the existence of gravitational waves decades before their discovery. Similarly, the framework of quantum mechanics relies entirely on abstract mathematics to explain the behavior of particles on subatomic scales. This power of prediction raises an intriguing question. If mathematics is merely a human intervention, why does it align so perfectly with how the universe operates? Critics argue that while mathematics is a powerful human-made tool, it is something we use to interpret the universe rather than necessarily reflect its fundamental nature. They propose that the patterns we observe may arise from physical laws rather than being purely mathematical constructs. Moreover, some point out that not all phenomena can be perfectly modeled mathematically, suggesting potential limitations of this approach. Others question the existential implications of the hypothesis. If the universe is mathematics, what does that mean for the physical perception of reality? Last but not least, our list concludes with the multiverse theory, which posits that what we perceive as the universe might be just one part of a vast collection of different universes. These other universes, often referred to as parallel or alternate, may differ in scale, structure, and even the fundamental laws of physics. To classify these ideas, the aforementioned physicist Max Tegmark introduced 4 distinct levels of the multiverse, each representing a unique expansion of our understanding of reality. At level 1, the multiverse consists of regions of space beyond our observable horizon. According to cosmological models, the universe is potentially infinite. If so, there exist countless regions beyond our visible space where the same physical laws apply, but with different initial conditions. In these regions, galaxies, stars, and even forms of life could exist vastly different from anything in our observable cosmos. Level 2 arises from the theory of eternal inflation. This theory suggests that rapid expansion of space gives rise to bubble universes, each with its own physical constants and dimensional structures. For example, one bubble might have stronger gravity, causing stars to burn out quickly, while another might have entirely different dimensions, making life as we know it impossible. These universes exist independently of ours and may remain forever inaccessible, separated by vast, inflating regions of space. Level 3 stems from the many worlds interpretation of quantum mechanics. This idea suggests that every quantum event creates a branching of realities, with every possible outcome occurring in its own separate universe. For example, when a photon passes through a slit, it takes all possible paths, each in its own universe. These parallel universes coexist, but are limited in their interaction. This perspective not only broadens the scope of reality, but also provides a framework for understanding quantum phenomena that appear probabilistic in our universe. Level 4 represents the most speculative level. Universes governed by entirely different mathematical structures. In this scenario, even fundamental concepts like space, time, and matter may not exist as we understand them. These universes might operate under completely alien rules, rendering them incomprehensible from the standpoint of our mathematics. This level is directly tied to the mathematical universe hypothesis, which asserts that all mathematical structures exist, and each corresponds to its own unique universe. Level 4 encompasses the idea that our universe is just one of an infinite number of mathematically possible realities. Here, the hypothesis of the mathematical universe serves as the philosophical foundation of the theory. If all mathematical structures exist independently of human thought, it follows that every conceivable mathematical structure can describe its own unique reality. This would encompass universes of all levels, linking the multiverse to the fundamental nature of mathematics. This connection raises profound questions. If our universe emerged from a mathematical structure, what determines its specific characteristics? And if alternate universes are described by different mathematics, could they ever interact with or influence our reality? Unconventional hypotheses, whether it be the multiverse, superfluid space-time, or the mathematical universe, challenge the boundaries of both scientific and philosophical thought. Critics highlight the lack of empirical evidence, as many of these theories are untestable with current technology. However, their conceptual strength lies in how they integrate mathematics, physics, and philosophy to reimagine our understanding of existence. These ideas prompt us to ask, are we nearing an understanding of the true nature of reality? Or do these hypotheses merely broaden our misconceptions? Perhaps to understand reality, we must first define what we mean by it. Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground, beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It is a marvel not only of engineering, but also of ambition, and a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, also known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of space, time, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but change it. CERN is nestled among the beautiful landscape of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground, the Large Hadron Collider, or LHC. This outstanding example of human ingenuity spans 17 miles, a circular tunnel in which the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang. By accelerating particles to near light speed and colliding them with each other, the LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it is also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows physicists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it is not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi element of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension, as shown in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions and particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics, literally. By analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limit of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey did not end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Another experiment called ALPHA has successfully trapped anti-hydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang Theory suggests there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, a fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but also pushes the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider from a chain of small gas petals. Each proton began its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas petals, gaining energy at each stage until they finally arrive at LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, that energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom and has a diameter of about 1 femtometer. By comparison, a mosquito is about 1/4 inch long. To visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well focused. The beams are carefully regulated or squeezed to ensure they collide in the detector at the point where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 tera-electron volts at even higher luminosities than before, meaning more collisions for data gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2202 mega-electron volt, which agrees well with the predictions of the Standard Model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe, the LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they have studied the behavior of the neutral D meson and neutral strange B meson, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomenon has been captured with unprecedented precision in recent data sets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations. which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into quark-gluon plasma. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosities, future data could further refine these measurements, potentially leading to new physics beyond the standard model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. Now, while the LHC can create tiny black holes, they are on the quantum scale and evaporate almost instantaneously through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific data. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. And finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, we want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. These areas of physics consider the possibility that our universe may not be limited to the three dimensions of space and one of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which both suggest that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multidimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and material science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. The ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our three-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions at the LHC where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It is planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe, from advancing our understanding of fundamental particles to creating new technologies. The implications to go far beyond particle physics, promising a glimpse into the very fabric of the cosmos and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time.